All right. 10:01 a.m. Everybody ready? Okay. Wow, there's a lot of you this time. How is week 2? How's week 2 going? Good? Good? Yesterday you talked about making JavaScript asynchronous, right? And how do we make JavaScript asynchronous? What have you learned so far? Set timeout? That's a good one. That's a good one. Any other options for making JavaScript asynchronous so far? Have you learned about passing callbacks yet? Did you talk about that? That's a fantastic way. I believe you'll learn about another way tomorrow as well. So, I haven't lectured to you before. Hi, anybody I didn't help last week? My name's Andy. I'm a mentor here as well as a lecturer. I like to start all of my lectures with a to-do list so that we have a list of goals and we have some accountability and we can come back to them afterwards and make sure that we've ticked everything off that we want to hit today. So, today's lecture is about networking with TCP and HTTP. So we're going to start off with a discussion about networking, which I believe you learned about yesterday, or did some readings about yesterday. Then we're going to introduce TCP, follow that up with a little demo. Then we're going to introduce HTTP and how it builds off of TCP. And then we're going to follow that up with a little demo. So to get started, obviously we're going to talk about networking. You learned yesterday. So what is networking? I also like to ask a lot of questions while I lecture. So, can anybody tell me in any terms what is networking? Communication. Perfect. In what sense? Are we talking specifically about computer networking? Are we talking about the networking where you're like on LinkedIn looking for different connections to find a job? What are we talking about? Right? Between computers. That's perfect. That's exactly what we are going to talk about. So it's essentially just communication, if I can spell it correctly. How is the font size for the people in the back? Can everybody read it? Perfect. Communication between machines on a network. And I realize that in the definition of networking, we're using the word network. But it's just a bunch of interconnected machines and how they communicate with each other. Okay, so as you can imagine, you've got all these disparate machines. We've got Macs, we've got PCs, we've got Linux, we've got servers, we've got routers, we've got switches. How do all of these machines, how are they able to communicate with each other? How is a Mac OS, if I launch a server on here, how could somebody connect from a PC machine? They're running a different operating system, they have a different file system. How would they be able to communicate, do you think? How would you communicate with someone that the two of you don't speak each other's languages? How would you be able to communicate with that person? Another language, yes. What you would call like a lingua franca, a language that you have in common. A language that you can both convert your native languages into and from. And that's how disparate machines can communicate with each other. In networking, we call this a protocol. What is a protocol? So we could define this as a defined standard. So if you're familiar with any other standards from any other industry like GMP, good manufacturing practice, HACCP, hazard analysis and critical control points, OFA, official first aid, things like that. These are all ISO, if you've ever heard of like ISO 9000 or ISO 9001. The International Standards Organization produces standards. Have you ever seen like a Purolator truck and on the sign it says ISO 9001? Have you ever wondered what that means? Never? Well, in short, it means that they have applied a standard, a standardized way of performing their job and they adhere to this standard. That means they have to keep certain records. They have to treat their employees in a certain way. They have to treat their customers in a certain way. And they have actually been certified to that standard. And the reason to be recognized in other industries to a standard is it shows that you are producing a quality good or service. If you're able to say, look, I have achieved a standard, then the people who consume your service know that you are at least that level, if not higher. Whereas if you don't have any certifications or anything like that, then people don't know what they're getting. You're just saying, I've got the best product on the market, and they're saying, prove it. Okay, so we have a defined standard, in other words, a standard way of doing things for how requests and responses are sent between network devices. Okay, so that's essentially all the protocol is that we have this defined standard way of if you want to send something from machine A to machine B, or from part of machine A to another part of machine A, how do those communicate with each other? What is the standard way of doing it? Because if you want to talk to someone else, and instead of using a lingua franca, a common tongue, you decide to invent your own language, they're not going to understand what you're saying, right? And what's the point of communication if you're communicating and the other party's not receiving what you're saying? Right? There's almost no point in that, right? So we have to adhere to standards, and hopefully today we can show you how these ones build logically on each other. Okay? Any questions so far about networking or protocols? Is everybody kind of following along? So far, so good? Okay. Awesome. Okay, so there are a couple different models that describe how networked machines or how the internet works. One of them is the OSI model, or the Open Systems Interconnection model. And this one was developed by the ISO, or the International Standards Organization, or as they like to say on their website, which I didn't realize, it actually stands for the International Organization for Standardization. So more than likely it is en français or something like that, and it's just translated. So the ISO. If anyone's interested, ISO is, they write all kinds of standards for all kinds of things. Food works to kind of a way of conceptually thinking about it, as well as breaking out who's responsible for what at each point in the system. And it might make more sense if we just kind of lay it out. So they usually start, ironically, with number 7. There's 7 layers. You can think about it like a club sandwich or like a lasagna. There's a bunch of different layers that are involved in this. So at layer 7, we have the application layer. At layer 6, we'll come back and we'll talk about these. I just want to get them all up on the screen so that I can do this thing, which I love to do, and really hammer home that point. That's equivalent to me like banging on my desk as me going, look right there. Okay. Number 5, we have the session layer. At number 4, we have the transport layer. Number 3, we have the network layer. Number 2 is, of course, the data link layer. And number 1 is the physical layer. Okay. So let's start from the top. If you had to guess about a conceptual model that describes the internet or how networked machines communicate, what do you think the application layer would entail? Have you ever heard of an application or an app? Okay. So what are apps? What do apps do? Just in the bare sense. They can do stuff for you. They user interface. There we go. These will be your user interfaces. These are any applications that are actually running on a machine. Maybe this is a node server. Maybe this is Minecraft. Maybe this is Slack. It's anything like that. Any high-level thing that's front-facing. It doesn't necessarily have to be front-facing to a user, but any application that's running. So we call these clients and services Or another word for services would be server. Services / server. So the way that we break this down is clients make requests for information, and services provide a response. They provide some kind of data or something like that. Okay? Stop me anytime if you have any questions about any of this. Okay. So the presentation layer is one layer below what your apps run on. Okay? So this would be something like the operating system. This is where things like encryption happens. This is where, so if these things are running on a high-level abstraction language, this is where that language is turned into ones and zeros. Because obviously your computer does not inherently understand JavaScript. The high-level programming languages that we use look like English because they're meant to be read by programmers. They're meant to be written by programmers and read by programmers. They don't actually mean anything to the computer. They have to be compiled or transpiled into something that means something to your computer, and your computer is a binary device that understands ones and zeros in a certain organization, okay? So this is where your JavaScript, your signals, your everything that comes down is converted to ones and zeros. The session layer is the establishing of a connection between two devices. There we go. Just fit on the screen. Awesome. Okay. So that's the whole purpose of the session layer, is to say, because the way that, is anybody old enough to remember a TV with rabbit ears? Okay. Is anybody old enough to remember radio? Okay, there we go. So the way that radio signals work, or the way that TV broadcasts work, or the way that even like Wi-Fi works, is it's just a continuous broadcast signal that's going all the time. And we decide to tune in. We decide to turn our radio on and change the frequency, and we can change the dial up and down, and we can tune in. But if we turn our radio off, does the radio station stop broadcasting? No. It's always there. And if we could hear that frequency, it would probably drive us absolutely insane, because it's going on all day. It's just outside of our hearing range. It'll be into the megahertz or the gigahertz range, way beyond what we can hear. But it's going all the time. But that's not how computers work. Computers can't just flood the internet with everything that they, like, hey, I've got a great site. Everybody want to hear about my site? That's not really how it works. The way that it works in computing is machine A communicates with machine B. And they have to establish a connection. And then once they're connected with each other, once this session, then they can start sending information back and forth. The transport layer. This is actually an aptly named layer. This is what splits up the network communication. So one thing that this one does for us, let's just go with communication so I can fit all of them on here. One thing that the transport layer gives us is ports. Have you heard of ports in networking or otherwise? Not to be confused with portholes, which are the holes on the left-hand side of the ship. On the right-hand side, they're called starboard holes, right? We good? No. Okay. So ports. Any device that what the transport layer does. So imagine that machine A is communicating with machine B, and imagine that you only have one pipe. And if you wanted to communicate with Google, you'd have to unhook that pipe and hook that pipe to Google. And then you want to unhook that pipe and hook that pipe to the Minecraft servers. That wouldn't be very effective. Your machine would only ever do one thing at a time, right? So to help us out with that, to enable multiple applications to utilize the same machine and the same network connection, the transport layer divides up your network connection into 65,000 plus. It's actually 65,535 ports. Has anyone ever heard of any famous ports that we use? If I visit www.google.com, I'm actually visiting a port. I'm actually going to that domain, but we have a default port. Can everybody see that? Let's move that up to the middle of the screen. This is a port number. This is saying communicate with google.com on a specific port, on port 80. And port 80 is probably the most famous one. That's HTTP. By default, a lot of these ports are locked down, just like radio stations lock down their signal. What did you say, the Beat 94.5? Because they broadcast at 94.5 megahertz, right? That's where you tune in. If you had another radio station broadcasting at 94.5, there'd be collisions, right? Your radio would pick up signals from both of them. So to avoid that, we've standardized some ports. And that's the royal we. I was not involved in this process much. Anyway, so we have some standard ports. Port 80 is HTTP. If you've ever heard of HTTPS, that actually goes over port 443. Okay, there's other ones. If we wanted to communicate with a Postgres database, the default port for that is 5432. And bear in mind that these are default ports. We can absolutely override these anytime we want. We can say, no, my HTTP server is listening on another port. It'll be on port 3000 or port 8080 or port 8000. We can define these ports. These are just standardized ports. So there are 65,000 of these that are available to our devices. And that's how you can have your web browser open, a game running, Slack going, Messenger running, and all these things are sharing your one network connection. They don't all need their own individualized network connection. Okay? So, yes? That's correct. Well, the transport layer divides everything up into ports. So it takes that network connection, and you get 65,000 ports per network connection. So if your device had multiple network connections, let's say you were connected with an Ethernet cable and you had a Wi-Fi going, then you'd have 65,000 times 2. Okay? So the network layer, one layer below that. So if we think about these top layers here, if we actually put a logical space, the whole purpose of layers 5, 6, and 7, the session layer, the presentation layer, and the application layer, is to produce and decode ones and zeros. By the time your communication, so you say, I want to log into Facebook. So it works its way down from the app through an encryption layer, turns it into ones and zeros, establishes a connection with Facebook if you don't already have one open. And by this point, your login should look like that. If you could see the network communication streaming, it'll all just look like that. It'll just be a whole bunch of ones and zeros. And what defines how those ones and zeros look? Protocols. There's protocols, remember that we mentioned up top. Your machine adheres to, or your application that you're running adheres to some kind of protocol. And every time it passes that data down a step, that adheres to a different protocol and a different protocol. And what they do is they divide up your data, send it to the other machine where they say, okay, that's this protocol. I know how to decode that data. And they decode it into something the other application can use or the other machine can use. Okay, so that is the whole purpose. This is where we play. This is where we as web developers play. Down here, we won't be so much. These are kind of like good to know. It's interesting to know about these layers, but we live in these layers for the most part, okay? So when it gets to this point, they're ones and zeros. What the transport layer does is it splits these up into what are called segments. So it will split up these ones and zeros in a logical way, and you'll hear me say this a lot, per some protocol. In fact, we call these are called protocol data units, okay, or PDUs. Is that still big enough? Okay. So we have divided this up into a data unit, and then it gets subdivided into segments. And the reason for segments is security and performance. When we send things over an internet connection, we don't necessarily want to send the entire block. When you visit a website, you're not going to get the entire code for the website all in one big lump over the pipe. Okay? So if you think about your connection to Google, you're not getting all that. You're getting it more like cars on a highway. And maybe those cars take different routes. Maybe there's an off-ramp that there's been an accident. Something's down, some router, some pipe is broken. They will choose a different route and find a better way to get to you. Okay? So all these ones and zeros will get broken up into segments per a standard by the transportation layer, and then they get handed to the network layer. Now, the network layer is actually communication between devices on a network. And the network layer will take these segments that get passed down from the transport layer and turn them into what are called packets, even smaller, little pieces of data. And then it will send it over the network, what we call the internet. Because obviously we don't have a direct connection. My computer is connected to the Wi-Fi, which is connected to Shaw or TELUS, which is then connected in some way, shape, or form to Google, let's say. So when I go to Google and I request information, we walk our way all the way down this stack, all the way down to the network, and then my device and a Google server are on that network. And we will exchange packets of information. You can think about it like a superhighway, and these packets are just streaming everywhere. That's exactly where packet loss comes in. That's exactly it. And this is the layer that also introduces something called IP. Okay. Does anybody know what IP stands for? You could probably take a guess what the P stands for in all of these. I even capitalized it. Okay, so we know what the P stands for. What do you think the I stands for, considering what class we're in right now? Sorry? Internet. There we go. Internet protocol. And what's the first thing that jumps to mind when you think of internet protocol or IP? What would you normally follow IP with? Address? Yes, IP address. That's exactly what the internet protocol does, is it sets up addresses for everything on the internet. We call these IP addresses. Most of them take the form of IPv4, which is the 192.168.88.195 or whatever. Okay, has everybody seen one of these at some point? Okay, so this is what the internet protocol does for us, is it provides every machine, everything that's connected to the internet has a particular and unique address. And FYI, let's see how many addresses. Let me know if I'm going too much on a tangent. How many addresses? Reserved IP addresses. There we go. Okay, so there are 2 to the power of 32. And if you want to work this out, each one of these is a number between 0 and 255. And the reason why that is because it maps to bytes. Okay? So each one of these is what we look at as humans. These are regular base 10 numbers, but they go from 0 to 255. So we have 255, 256, times 256, times 256, times 256. And that gives us 4.2 billion possible IPv4 addresses. So what's the next logical thing? There's far more than 4.2 billion people on this planet, right? And each one of us has multiple devices. You've got your laptop, you've got your cell phone, maybe you've got a desktop, maybe you've got a smart TV, right? So we have long ago exceeded this 4.2 billion unique addresses that are provided by IPv4, okay, that look like this. So the way that we get around that is every internet-facing device gets its own unique, so like our router has its own unique address, but we don't have our own unique address. When we communicate with the internet, we talk to the router, and the router talks to the internet. And it keeps track of who asked for that information. So when I make a request to Google, it keeps track of who made that request. Then it sends that request to Google, and then it comes back. And then when it comes back, Google says, OK, this IP address asked. I know what the source is, and I know what the destination is, so everything gets routed. So you're saying, I want to drive from here to Chilliwack. How am I going to get there, and how am I going to get back? OK? So, but instead, it's our router to Google servers. OK? And Google figures out the response, whatever it's going to be, whatever the response to our query is, and it's going to send that data back. And when the router gets it, because that's who Google thinks they're communicating with, when you say, what's my IP address? If you do this right now, yours will probably be the exact same. Because this is whatever is the internet-facing IP address. OK? So this is what Google thinks they're talking to. This is the IP address of the router that I'm connected to. OK? So what happens then is that it comes back. Google sends everything back to here. And our router says, OK, who on the network asked for this information? Oh, right. It was this machine here. Send the data to that one. OK? Everything kind of making sense so far? This is more of a conceptual lecture than like a hands-on. This is just conceiving of how the internet kind of works. OK. We have two more layers. We have the data link layer. And this is actually how physical devices connect to the network. OK, so this might be an Ethernet cable. This might be a Wi-Fi signal. This might be Bluetooth. This is how, if we introduce the physical one, can anyone guess what the physical layer would be? The hardware, exactly. These are the actual devices themselves. These are the cell phones and the laptops and the servers and the routers and the switches. This is the only thing in this conceptual stack that you can actually touch and feel. These are real things. All of this is the network, our internet, and how that all conceptually works. And tying the two together, tying the physical with the virtual, the logical world, is this data link layer. Okay? And then at the very bottom or the top, depending on how you look at it, we have our physical devices. OK, so that is the OSI model. And that is not the only logical model. Does anybody have any questions about that? Any comments? Does this challenge the way that you thought about the internet? Did you ever think about how the internet worked before? Yes. Well, it depends on what you're trying to hack. The broadest definition of hacking is using something in a way it was not meant to be used. So it depends on where you want to hit. If you were trying to, the presentation layer is where encryption happens. So you might try to get in between. If you were doing a person-in-the-middle attack, you might get in between the application layer and the presentation layer. Or you might get in between the application layer and the network and transport layers. And spoof. This is what people do with the person in the middle. You'll pretend to be the router. You'll go sit in Starbucks, and you'll set up a router from start broadcasting from your machine, and people will see in their Wi-Fi connection, oh, Starbucks, and you click on it, and then they've just actually connected with your machine, and they're routing through your machine to the internet, and you can see all of their communication, as long as it's not encrypted. That's how person-in-the-middle attacks work. Does that kinda? Okay. We don't deal with hacking in this course. There's actually, it's a common misconception of people outside of the industry that think that all of us know how to hack. They think that that's exactly what we are. We're just a bunch of hackers. Very few programmers actually know, beyond like the rudimentaries of like URL hacking, how to hack. In week 5, we do SQL injection, which is the #1 way that websites get hacked. So that's always fun. But okay, any other questions about the OSI model, why this was developed, anything like that, before I show you another model to kind of hammer this home? Are we good? Okay. So we have another model that describes how the internet works, and we call this the TCP IP model. And this was actually created, this model was created by the people who created the internet. And who are the people who created the internet? Does anyone know? History lesson. If you said the military, you are absolutely correct. It's the Department of Defense for the US. They were concerned during the Cold War that a focused nuclear attack would destroy their chain of command. If you were thinking about there's one person who can give orders to an army, there's one centralized library of information and resources, and what if that gets nuked? Your armed forces don't know how to communicate with each other, no one knows what's going on, where are the launch codes? They didn't want this kind of thing to happen. So how do you handle a single point of failure? If you think about it logically, how do you handle a single point of failure? Anything? The answer in networking is redundancy. You have redundant systems set up in multiple places. So if you spread these centers of information around the United States and ultimately the world, then there is no single point of failure. If, heaven forbid, somebody wipes Washington, D.C. off the map, then the whole thing doesn't fall apart because that was just one node on a network. So this was actually created by the Department of Defense. That was their entire reason for creating the internet. And it was entirely for secure communication, sending of documents and information. And that will become kind of clear when we start talking about what exactly, I know, 1034, when we finally get to what exactly TCP is. Okay? So this conceptual model has less layers. This model has an application layer. We'll just number them for fun. And this application layer in this model wraps all 3 of these layers together. So the session layer, the presentation layer, and the application layer get wrapped together. Okay? So like I said, if we thought about a logical distance, this is where we play as developers. So when they were coming up with their model for the internet, they said, okay, all of you programmers, this is where you live. You live in the application layer, so let's just put all of that into the application. So this is clients and services and encryption going on here. So everything that happened in these 3 layers. Oh, and the session layer. Okay, underneath that, we have, again, the transport layer. And the transport layer is responsible for splitting up our communication, our network connection, into ports. Okay? Exactly the same idea. Beneath that, since these are the people who created the internet, they don't call it the network layer. They call it the internetwork layer. Okay? exactly the same thing. It just means interconnected devices, right? Inter just means between. It's the same root that gives us like intersect, interest, and stuff like that. Inter means between, network, internetwork. This is where we get the word internet from. So this is just communication between devices on a network. Okay, and then number one, again, they just gathered these things together. They tied layer 2, the data link layer. Remember we said that data link was how devices actually connect to the network, and the physical layer together. And they call this one the network access layer. And this is the physical devices and how they connect. Oh, and wrapped. Okay. To the network. Does this model make more sense, less sense? Do you see how this compares conceptually to the OSI model? Yes. Oh, okay. All the way up this particular layer or in the TCP model? Okay. So the application layer is where your actual applications will live. These will be the things written in high-level programming language, languages that are human readable, like C, C++, JavaScript. This is where your HTML and your CSS live. These are high-level languages. So these will be servers and clients, the services and clients, anybody who's offering up data or consuming data. Because what's the point in connecting to an internetwork if you're not actually going to share data across that internetwork, right? Okay, beneath that we have the presentation layer. This is where your operating system lives. This would be Linux or Mac or Windows. This is also where all of the encryption happens, because this is where JavaScript or HTML or CSS gets turned into ones and zeros. Okay, so this is the moment when it will be encrypted or decrypted. Okay, that's what happens in the presentation layer. And then the session layer is actually establishing a session, in other words, a communication, a chat time between two machines on the network. Okay, that's all the session layer does, is just establishes that connection. So in the TCP IP model, they just wrap that all together. Okay. Any other questions about this conceptual idea of how the internet functions? Okay. So why don't we move on to, so is everyone clear on the need for protocols? I know we haven't talked too much about specific protocols, but is everybody clear on why we need to enforce rules for when we communicate with each other? Okay. All right, so let's move on to TCP. So what, all caps, what is TCP? Okay, you could probably guess what the P is, right? So I'll give that one to you. I'll give you another clue. It lives in the transport layer. TCP lives in this layer here. So can we guess at what the T stands for? Transport, perfect. And the C is for control. So this is the transport control protocol. It controls how we transport. Actually, let's talk about, there is another one that might make this a little easier to reason about. Transport layer protocols. Okay, so as we said, the whole point is of this layer is to establish ports for our network connection, right? So that we can have multiple applications running using the same one, right? And it is also to break our data from ones and zeros into segments for transportation. And it gives these segments a source and a destination. So if you were going to cut up communication, if you had a message to deliver to somebody and you were going to cut it up and give it to multiple different messengers to take to that person to be reassembled into it, you'd want to include the destination address, right? You'd want to say, this is where it's going. If anybody gets lost, this is where you're going. But you also include the source, because there's no point in yelling over the internet, right? You need to know that it got there. So we also include a source so that Google knows when I make a request to Google, it sends it back. It doesn't just go, okay, I've got your data, whoever asked for it. So every segment that gets broken up will have a source and a destination. Where did it come from and where is it going? That way, when it gets received, it knows where to send it back to. Okay? So there are 2 protocols in here. There's another one as well. UDP. You can probably guess again what the P stands for. The U and the D, I couldn't even tell you necessarily why it's called that. But this is the User Datagram Protocol. OK. So what are some advantages of UDP? Is this like the most fascinating lecture ever or what? OK. It may very well be the only theory one you get. We'll create a little server later, something fun. I'll wake everybody up when we get to that point. Okay, so UDP, what does it do? Well, it's got a very small header size of, let's see, what is it? It's 8 bytes, which results in smaller packets. If we look at TCP, TCP has a bigger header size, was 20 bytes. Okay, so UDP has a smaller header size. It's a much more focused protocol. Okay, so it will produce smaller segments, which produce smaller packets, and so it communicates faster over the internet. Because obviously, the amount of data you want to send is how fast you're going to communicate, right? If you want to send smaller things, like if you're driving a smart car down the freeway, you can whip around all these other trucks, right? Whereas if you're driving a big truck, you have to be worried about, oh, I can't fit into that spot. Oh, I can't fit into that spot, right? OK, so it is what's considered to be connectionless. It doesn't care necessarily whether a connection is even established. If it gets a request, so it essentially ignores this session layer to a certain degree. It will, as far as it's concerned, it's like a hose. It would be like, I've connected to this server, it's serving information, and the server just goes, OK, and it just floods it down the hose. I like to think about it like, you know when does everybody still have backyards? You know when you hook up like a garden hose, you hook it up to the tap, and the other end's not hooked up to your sprinkler yet. But you're like, I've got 40 feet of hose. I can turn the water on, and then I'm going to run over there before the water gets to that end of the hose, and then we're going to hook it up to the sprinkler and put it down, and then my job's done, and I don't have to go back to that tap, right? And what happens if you don't make it there on time? Well, it starts pouring out, right? Like this water's pouring out, and you're like, I got to connect to the sprinkler. And then you're like, next time, I'm going to go back and like make sure this is off and do it properly, right? Hopefully, because you get completely soaked. This is what UDP, this is actually how the user datagram protocol works. It's fantastic for streaming music or video, where we don't really care necessarily if we lose some packets, some data gets lost along the way. You see it in videos. You'll see like all of a sudden it becomes like blocky, or it's missing a frame, or your Spotify stops and then it starts up again. Those packets just got lost somewhere along the way. And it has, so obviously TCP establishes a connection, and we'll talk a little bit more about that in a second once we're done comparing the two. It has no error recovery. So if a packet gets lost along the way, It's like that water coming out of your hose. It's just on the grass. It's wherever. It got lost along the way. They don't even try it. They don't try and send another one. They don't confirm, hey, did you get that one? They're just throwing packets down the pipe as fast as they can because they want to stream Twitch to you. They want to stream Spotify to your phone. And they just want it to happen as fast as possible with as little latency as possible. Latency is the time between something happening and you perceiving it happening, right? And you want video, live video, to be as low latency as possible, okay? Right? So there is no error recovery on this. Whereas with TCP, missed packets are resent, okay? Let's put a hyphen in there. There we go. So it doesn't look like they resent it for some reason. Okay. You know, as an aside, you know what my absolute favorite programming term is? Subversion. Because there's no hyphen in there. So I always read this as subversion. As in like to subvert something? Yeah, yeah. I feel like there really should be a hyphen in there. Anyway. That was an aside. Okay, what else do we have here? With UDP packets, we've already established that our data is traveling in these little cars. They're carrying it around, packets on the superhighway. So packets can arrive in any order with UDP. Some parts of the video will show up. Other parts, maybe they got lost. They show up afterwards, and it kind of gets descrambled as best as the higher layers can do. But this is where you see dropped frames, you get crackling on voice over IP, stuff like that. This is because the packets can arrive in any order and there's no error recovery. Here, with TCP, packets are guaranteed to arrive in order. And that is not necessarily true, but it's true on how they hand it off. The packets may arrive via TCP. They may go over the network layer and the transport layer in any order, and they arrive. But what the transport layer does is it makes sure that it assembles them all back together again into a coherent package before it passes it back up the chain to be decoded. Okay, so that's what TCP provides for us, is logically puts it all back together. Whereas UDP goes, yeah, these just showed up. As they showed up, I'm just giving them to you. Okay. And what else do we have? Yeah, okay. So this is incredibly useful for streaming of any kind and or low latency applications. So anytime you need extremely fast communication and you don't really care whether everything gets there or not, okay? Whereas TCP, so the packets are guaranteed to arrive in order, and it is useful for guaranteed communication. Okay, so let's say you're setting up a Twitch kind of clone. Which communication method do you think you'd want to use? UDP. Let's say you're setting up a banking website where people have to securely connect to your site and you don't want people getting in who aren't authorized. You don't want people seeing information they shouldn't see. Which one would you use? TCP, exactly. So you can see why the Department of Defense created TCP. Because they wanted secure, guaranteed communication. Right? They couldn't just rely on streaming launch codes over the network and hoping they all get there in one piece. So we typically use, as developers, we'll typically use TCP because we want to make sure that our packets arrive in order, that a connection is established, and that any missing packets are resent. Okay? Because imagine that they don't get a part of your login information. Well, you want your computer, you want that other side to say, hey, I seem to be missing a packet. I got all these packets are numbered, and I'm missing number 7. Can you resend number 7? And then your computer will go, oh, yeah, here you go. There's number 7 again. And then it goes, ah, thanks. I can put this all together again and descramble it, and you can log into Facebook now. Okay? So this is what the majority of our servers will communicate over, is TCP. So what is, let's see, what else do we get from TCP? Establishes a connection. Okay. So this is what is known as, and I can never remember this, is it the three-way handshake? There we go. Okay. So it is the, they call this the three-way handshake. So the way that, remember when I said that TCP establishes a connection, whereas UDP is kind of like, it's just point and shoot. It's like somewhere over there, they asked for information, I'm just going to send it to them. Whereas TCP goes out of its way to establish a connection between the client and the service, whatever that service is. Maybe it's a web server, whatever it is. And so they actually do a three-way handshake. And what this is, so in a traditional handshake, one person extends their hand, the other person extends their hand, they shake, right? So the way that TCP makes a handshake is it sends a request over the network, and it says, hey, I want to go over the internetwork, and I want to communicate with the Google server. So my computer says, I type in www.google.com, and I send a request over the network. So that's me extending my hand. Google receives that connection, the Google server, and it sends back an acknowledgement. It says, I see your hand there. Then it sends back a request. It says, I would also like to shake your hand. Would you like to shake my hand? And then that request comes back to my computer, and my computer sends back an acknowledgement that says, yes, we can now shake hands. And that's why it's a three-way handshake, because I make a request, Google receives that request, acknowledges it, sends back a request to shake hands, and I receive that, and I send back an acknowledgement and say yes. Okay? So you can see that TCP goes way out of its way to make sure that that connection is established and solid, and everyone's communicating on it. Okay? And to hammer that home, let's see if we can find, there's a TCP joke. Hopefully we get one that's reasonably clear. Is that big enough? Hi, I'd like to hear a TCP joke. So imagine this is the client. Hello, would you like to hear a TCP joke? Yes, I'd like to hear a TCP joke. Okay, I'll tell you a TCP joke. Okay, I will hear a TCP joke. Are you ready to hear a TCP joke? Yes, I am ready to hear a TCP joke. Okay, I'm about to send a TCP joke. It will last 10 seconds. It has 2 characters. It does not have a setting, and it ends with a punchline. Okay, I'm ready to get your TCP joke that will last 10 seconds, has 2 characters, does not have an explicit setting, and ends with a punchline. And then the server replies, I'm sorry, your connection is timed out. Because they realized they needed to end with an actual joke. But I wanted to highlight to you just how pedantic TCP is. This is how all of our communication goes. I'm going to send something. Are you ready? Yes. I acknowledge that. I acknowledge that you're going to send me something. I am ready to receive it. Okay, I'm sending it now. Okay, I'm still ready. This is how TCP works. I just want to hammer this home because HTTP, which is where our programs live, HTTP and HTTPS, they use TCP under the hood. And a lot of the things that we say, HTTP has this, it's actually because TCP has this. And that's why we're spending time today talking about TCP, even though you're probably never in your career is going to be concerned about TCP. It's going to be one of those things that just happens under the hood. But if you want to understand why things above are restricted, you have to understand how they're happening down below. Okay? So there's our TCP joke. There's also a UDP joke, which I don't have to look up and show on the screen. It is, I would tell you a UDP joke, but I'm afraid you won't get it. Thank you. I appreciate it. Yeah. What are we looking at? 10:55. Okay, does anyone have any questions? We'll move on to a practical demonstration after the break. Does anybody have any questions about TCP or these conceptual models of the internet or how the internet works?
So if we play games, right?
Yeah.
I understand like you want to minimize
Mm-hmm.
But then you also want it to be secure so that people can't, you know, like go into like to be able to go into to compromise like servers.
Mm-hmm.
So how would they kind of compromise between getting the security of TCP,
Yeah.
but utilizing the fast connections with UDP?
Okay. So the great thing about this is that these are handled by different layers of the cake. Okay. So UDP and TCP live in the transport layer, whereas encryption lives in the presentation layer. So the whole thing about TCP versus UDP is TCP makes sure that that handshake is solid and that the connection is solid and nothing's going to get lost, whereas UDP just sprays and doesn't care. But it can still be spraying encrypted information. And that will get decrypted by another layer once it gets received. So yeah, don't conflate those two. All we're talking about here is how our data gets from one end to the other end. And the big difference between TCP and UDP is this is lossless because of the fact that it goes to so much effort to make sure that the connection is solid. Whereas this one is just, it's over there somewhere. You said you wanted to watch this stream. Here's the stream. I don't care if anything gets lost. Don't bother telling me if anything gets lost. Yeah. Yes. Yeah, absolutely. The only limitation over the network connection is your device set up to listen for this protocol on this port, and is the other device set up to listen to another protocol on a particular port? That's the only limitation there. Other than that, you can send it over many different layers. And you may see applications that have, maybe they have a larger user interface that uses HTTP or TCP to control like user login and log out, establishing friends, maybe sending messages. And then they'll use UDP to live stream into a window inside of that application where they don't really care about necessarily whether it's encrypted, whether there's loss or anything like that. We good? Any other questions? Cool. We'll come back and we'll set up a net server in 10 minutes. Hi. Oh, yeah. All right. Are we ready to jump back in? You can run ifconfig in the terminal. And if you can probably also find it through the UI. But if you type in ifconfig, then you'll see under whatever your main connection is, that there will be an inet. It'll be, mine is EN0 is the connection that I'm looking under. And then you'll have an inet address. And that is actually your address. And the only thing that's different between yours and mine will be these last 3 digits. Yeah, and I'm 190. So this is our subnet. This is the subnetwork that's created by our router. And then each one of us gets our own individualized. That's how the router knows where to send internet traffic, in particular, where it goes. So each one of us will have a different 3-digit code on the end, but we'll all start with 192.168.88.
So basically, the big IP address from the router is like an umbrella for all of ours.
That's exactly right.
We'll always have separate ones, so it's like an umbrella. The one big one covers all of us.
That's correct.
And then we all send it back to the umbrella.
Yeah. We call this a subnet. So it's a sub-network. And so this is IPv4, and this is the limitation of IPv4 only having 4.2 billion address possible combinations, right? So they've actually created an IPv6, which you see right here is INET6. And these are actually hexadecimal codes. And there's it's power of 4 more. So it's 4.2 billion to the power of 4. And so more addresses than we will ever need to use. But unfortunately, in order to use IPv6, a lot of networks would have to change the way that they work. So under IPv6, every single device would have its own unique address on the internet, rather than going through networks and subnets and things like that. And if you're really interested, June 6th is IPv6 Day. So it's when everybody gets together and says, hey, remember this protocol that we wrote in 1995 and still haven't adopted? It still exists. One day a year, we remember it, June 6th. But yeah, we're hoping for adoption of IPv6, but it would mean that a lot would have to change about how the internet currently works. Because the internet is set up to use IPv4, because when they came up with IP, they didn't think 4.2 billion people would ever use the internet. Okay? I had another question over the break concerning how ports work. So another way to think about ports is, if this is your address, okay, this is your IP address, you can think about this as like the street address of an apartment building. Okay? Whole bunch of people live inside that apartment building, all in their own discrete units, but they all share the same address. What's different about them is their unit number. So you can think about the port like somebody's apartment number in an apartment complex. Everybody has the same street address, but then to get the mail to your unit, they have to put in your apartment number. So you can think about it like that. This is your, as far as the internet is concerned, this is your address, but maybe you're communicating on port 3000 or port 80 or port 8080. And that's how it gets divided up. So does that make more logical sense? Okay. And if anyone's interested, just super quickly, this is not human readable, right? If you had to type this in every time to go to www.google.com, but you had to type in 254.111. That doesn't exactly work. So does anyone know, has anyone ever heard of how this is converted to human readable? Why can we type in, if the internet works by internet protocol, how come you can type in facebook.com into your browser and you go to Facebook? Facebook.com is not a valid IP address. The IP address for Facebook will look something like this. It absolutely will look like this. has anyone ever heard of how this happens? That's exactly right. DNS, or Domain Name Service. And so what actually happens when you type in facebook.com into your browser is your browser doesn't immediately go and look for Facebook. It needs to know that IP address in order to communicate. So your machine and your internet provider have a very small amount of IP addresses that they know off by heart. And these are addresses to what are called domain name servers. And the whole purpose of a domain name server is you say, hi, what's the IP for Facebook? And they respond with some kind of IP address. And then your computer makes a request to that IP address. Your computer doesn't know where all of these things live in the world. We have to ask these massive databases known as domain name servers, utilizing this domain name service. And all that does is it's literally tables with 2 columns. Facebook maps to this. Google maps to this. Your personal website maps to this. And that's how we get to the point where we can use IP to communicate. Okay? All of this happens behind the scenes. Your browser does it automatically. It just reaches out to any DNS. And you can set these up. If you have a VPN, the way that the VPN works is it uses different DNSs to jump around and hide where you are calling from. Because if you just use your computer connected to your internet provider connected to the internet, then everyone along that chain can see everywhere you go and everything that you do. It'll be secure if you're using HTTPS, like it'll be encrypted, but they can still see, oh, you made a request to this domain. Whereas if you use a VPN, then you point to somewhere else, and that points 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 to Facebook. Does that make sense? That's how VPNs work, to hide where you're from. Okay? So that was just a little aside. So now we're actually going to do some programming. We're going to move on to our TCP demo. So we're actually going to do this in, I don't like the way these windows are organized. We're actually going to use the Node net package. Okay, you've spent some time, can anybody tell me what Node is? Does anybody know what Node is? You spent some time utilizing Node, right? You type node whatever.js into your command line and it runs. What is Node? It is a library. It is the browser's V8 engine running in the command line. They took the V8 engine, which is the thing in the Chrome browser that converts your JavaScript into ones and zeros and back and forth and things like that, the thing that actually makes stuff happen. They took it out of the browser and they put it on the server side, and that's what Node is. But there's other things that need to happen in a web server that doesn't need to happen in the browser. And one of those things is communicating over TCP. The browser will never be responsible for that kind of low-level routing, right? But a server may very well be responsible for that. So Node has a package called net. And we're going to utilize this net package to create a little TCP server. So one of the things you've dealt with, actually, how much time do we have? So I have one already coded up, and maybe we'll just look over the code together. OK, so have you dealt with NPM, the Node Package Manager? OK, so internal libraries do not need to be NPM installed. OK, I didn't set up, if we look at the directory that I'm in, ls-l, you see that all we have is a README and the TCP folder that I'm in. You don't see a node modules, you don't see a git ignore, you don't see a package.json. Okay? This is the built-in net library. It's built into Node. But they don't offer it up all the time. We have to voluntarily say, we want to bring in some functionality from that. So in an effort to keep Node lean, they don't automatically load all of the packages. Okay? You have to explicitly say, I want this package. Because otherwise, you get all of Node every single time you tried to run something. Okay? But we don't need to run npm install, and you also won't be able to type in npm net and try and find it because it's not actually served on npm. This net package, this is a totally different package. Okay? If you want to read about it, you have to go to the Node documentation. Okay? And that's actually where we are right now. We're at nodejs.org to find that. And you can see, let's see if there's, you can see other ones. There's HTTP, HTTP2, HTTPS, file system, and events, and things like that. Node has a whole bunch of packages built in that you can utilize to do things. Okay? So, first thing we need to do is we need to require it, right? We want to bring in any kind of package when we're in the server. When we're in node side, we need to require it, right? I'm setting up a port. Arbitrarily, port 3000. As I said, we have 65,000 ports to choose from. Does anybody have a different port that they... 3000 is just as good as anything else, right? So we've brought in this net package, and we want to create a server. We want to set up, in this case, it'll be a TCP server, but that's kind of abstracted away from us. So guess how we create a server? We call net.createServer. Right? OK. Let's see here. Can I make this smaller? Let's comment that out for right now. Actually, let's get rid of this. We can always come back to this. Server.onConnection, client connected. Let's get rid of, actually, let's just comment it out for now. Comment. That should be fine. And then comment all this. There we go. OK. So we say const server equals net.createServer. So what this does is it gives us a TCP server. Okay? It's set up with all of its default values, but it's not actually listening to anything. In order for a server to actually work, we have to call server.listen and specify the port to listen on. Okay? You'll see this very commonly in Node packages. It'll be server.listen, app.listen, things like that. And we pass in that port variable that I defined up here. You could also just pass in, if you wanted to set it up, you could just pass in a port. Whatever you want. You could pass it in. You could pass it in as an integer. You can pass it in as a string. Any of these are valid. So I'm going to go with port 3000 that we set up here. Okay? And that is, if we comment everything else out and comment this out, there we go. OK. So we literally have 4 lines of code in this file. We bring in the net library. We set up a port. We create a server. And then we set our server to listen. OK? That's all we have, 4 lines of code. OK? And let's jump back to the terminal. And we'll run node. Okay, clear. We'll clear this side as well. There we go. And we're going to run node TCP/server. Hopefully that's not too small. Can I make that bigger? OK. Is that too tiny for everybody in the back? And run the node server. OK. So you've run enough node applications, hopefully by now. What's happening? It is. It's actually just sitting there and listening. The way that node works is if there's any underlying process still running, the node application will not close. So since we asked this thing to listen, our connection isn't closing. Our node application is continuing to run. If I want to stop it, I have to do Control-C. Okay? If we take this line out and run our app, it will run and it will stop. Okay? To actually get our underlying process to run, we have to call server.listen. And now we have a node server running. Well, can we prove that? Sure. OK. So in order to be able to figure out what's running on your network, you can run netstat. You probably have to install this. I had to run brew install in order to get netstat onto my machine. But you can see that netstat gives us an absolutely stupid amount of information about what's currently happening on our system. And you can start to see some of this. Don't worry, I'll break this down in a second. But you can start to see, hey, that's communicating over a protocol. See this proto? TCP. That sounds familiar. UDP. That also sounds familiar, doesn't it? OK, so if we look at the man pages, actually, you know what? Let's open a new terminal so we can see this larger. Are you actually going to? OK, we're going to open a new window. And if I run netstat in here, you'll see that we have all this massive amount of information, right? Has anyone ever looked at the man pages? Man pages are manuals, that's where the man comes from, that are actually in the command line. And for most applications, someone has written a user manual that you can access with man and then the name of the application you want to use. So you know how you can run ls? You can run ls and you can see all the things that are in your directory, right? But if you want to do something else, you can pass an argument, right? You can pass ls-l, and then you'll see everything in a long list with some extra information that wasn't there before. And if you want to see hidden files, you can use a, and then we'll actually see all of the hidden files that are in the directory, as well as the dot and the dot dot. Those are actually commands. That's how you're able to move between directories, because those are actually commands in the file system, dot and dot dot. OK? So the same way that we can do that, we can pass arguments to netstat to filter down what we want. And there's a couple that we want to see. We want to see -v to increase the verbosity level, the verbosity level. Verbose in computer programming means I want to see more information. OK? There's another one that we want to see, which is A. Show me all of the active ports. OK? There's another one that we want, N. Show addresses as actual numbers. OK? And then P, we can specify a protocol. So having all that in mind, we can simplify this output down to something that we're actually interested in. So netstat-v, we want to increase the verbosity. We want to see more information. We want to see all of the ports, all the active ports. We want to see them as numbers. And we want to listen to a protocol, TCP. And we get a much more condensed list of what we're listening. So we're looking at all of these TCPs, right? OK? And there we see. So if we start our server, node TCP server, and then we rerun this, we see that we now have a server running on the local address listening. OK? And so we have this as our number one. It comes up as TCP 4.6. In other words, it's communicating on level 4 and level 6. And if we close this off, we kill this, and we jump back and we run netstat again, you see that one's gone. OK? So hopefully I've just proven that we were actually running a TCP server that was listening on port 3000. OK? Now, what good is a server without actually being able to communicate with it? So let's kill this process. And we'll come back and we'll uncomment some of this code. So if we look at the documentation, you'll see that there's a whole bunch of events that we can listen to. Did you learn about events yesterday? Events are a way of handling asynchronous code. We can listen for particular events to happen. They may happen at any time. And then we can specify a callback function to run in reaction to these events. OK? Does that make sense? That's how we take our JavaScript and we make it asynchronous. OK? So let's start with the error event. So when an error happens on our server, we can listen for that. And the syntax that we use is server. Remember, we defined our server as net create server, right? We're saying that server.on error. So we're naming the event. If this server encounters an error, then run this callback function. Run this anonymous arrow function that I've passed in there. Okay? This should look familiar from yesterday, how we handle asynchronous. We're saying if there's an error, then console log the error. And I can actually change this to console.error. There we go. Did you know that there's other things besides console log? Okay. It's console error, console info. All it does is just change how it shows up in your console. Okay? So we're saying that if the server encounters an error, then show that error on the console. Okay, so that's great. But what about if we wanted to listen for a connection? Wouldn't that be fun? And then we could, so the connection, so server.on, you'll see that this is a very, very common syntax. Whatever happens, .on, the name of the event, and then the callback function to execute should that event happen. Okay? And so we're saying that when someone connects, we're going to console log client connected. Okay? So let's test that out. If I get my server running, there we go. And then I'm going to use an old protocol called telnet. And so we're going to telnet. We have to pass in, oh, why did I clear the screen? That was dumb. We pass in my IP address and the port that I set up. Connection closed by the foreign host. Fantastic. Why did that happen? ifconfig. Pipe that to grep and inet. Is that not my inet? 192.168.88.90. Wow. Okay, so we're not going to use telnet. Instead, we will set up our server. We'll set up our client. Clear. Node. TCP client. What is happening? This is not connecting for some reason. Let's try that again, and try that again. We're not actually console logging any connections. Interesting. Okay, we'll try and flesh out the code a bit, and then we'll see what's going on here. Server.on. Maybe we'll choose a different port. Try 3001. No TCP server, and set this up. Wow, it just really doesn't want to connect. Connection refused, unable to connect to the remote host. Fantastic. This is what every lecturer loves to happen. Okay. If I uncomment everything out, is it going to run as expected? And uncomment all of this. Set the encoding, push the connection, and connections array, and then cool. Is that going to work? Well, it's not stopping, but it's not registering any of the connections. Oh, because we're on 3000. Let's try that again. Kill this, start that back up. We're not getting any output at all here, but no errors. Wow. This is incredible. Okay, let's try net.js. Let's try and do this just from the ground up. No, that one. There we go. Okay, const net equals require net. Const port equals, let's go with 8080. Const server equals net.create server. Server.listen on port 8080. Okay. node net.js. Okay, that's running. Telnet 192.168.88.190 on port 8080. Yay, I'm in. Perfect. Okay, so this is actually working for some reason, and the other one is not. Okay, so we are going to listen for server.on connection, and we're going to pass in a callback function, and we're just going to console.log client connected. Just for right now, let's kill this. There we go. Start that, and start this. And here we see, at long last, a client has connected. Okay, and if we do that again from another window, what did I say, 8080, we'll see, hey, another client has connected. So we're actually able to establish a connection to our client, to our server. But that's not super good because we're not actually able to receive data or anything, right? So we can actually accept a parameter called connection. And we have a couple different options to do on this connection. One of them that we can do is we can write to the connection. So if you think about this connection, remember I said that the session layer establishes a connection between two machines? So this is what that connection actually is. And we can actually write directly to this connection. So we can say, hello from the server, just for interest's sake. And we'll kill this. And you notice that killing the server disconnects all of the clients. You'll see on this side we have connection closed by foreign host. Okay? In other words, the host shut down, so my connection terminated. You can't maintain a connection when one of the sides drops off. Right? Okay, so now we're going to start our server. And now whenever a client connects, we get hello from the server. Okay? We were able to write to that connection. When we start it up again over here, even bigger, we see hello from the server. We're actually able to write to that connection. Okay? So why don't we put in a new line on the end of that so we get that. And then we can do other things as well. Because what event might we be interested in? Well, how are we doing for time? Is there data coming over the server? Okay? We write a callback function. That's how we handle asynchronous nature. And we can console log from client and console log that data. So why don't we see what happens to this? We'll kill our server. We'll start it up again. Okay, client connected. Hello from the server. And then we're going to type something in. From the client, we got this buffer. Well, that's odd. What if we connect from this client? Hello from here. Oh, wow. Look at that. So the data that we got is a buffer. So we're actually looking at the raw data encoded in hexadecimals, but this maps to the characters that we type in. This is H, this is E, this is L, this is L, this is O, and this is the carriage returns, right? So you can actually, all of this maps to literally what came over. But again, that doesn't really do anything for us, does it? So we can actually say connection dot set encoding. Has anybody ever heard of character encoding? Character encoding is simply the way that characters are turned into hexadecimal or binary code. So we have a famous one, UTF-8. Okay? So we're saying that on this connection, set all of the encoding to UTF-8. So if we kill this and run it again, you know what? Why don't I close this window so we can see this nice and big on the... Okay, clear. Okay, so this is our server. It's running. It's listening for connections. I have to keep jumping back and forth between the two windows. And we're going to set up our telnet connection on this side. So now when we type in hello from the client, we see from client, hello from the client. Okay? That is, notice how it was a buffer before, and now it's not a buffer because we told it, we want you to descramble that buffer using UTF-8. Turn that into human readable content. Okay? So And you can see that what actually happened is from this side, when we sent that over, it actually went down and got encoded and turned into ones and zeros, transferred over to the other machine, and then was turned back into hexadecimal code and then back into English again. Okay? We didn't actually, changing the encoding does not say send this over as English. It still goes over the line as ones and zeros. And what we're saying is when it comes to descrambling it using this standard. Okay? There are other standards that you probably heard of, like ASCII and things like that, right? UTF-8 is very common for the internet because it handles a lot of special characters that happen in non-English languages. Okay? So that, in essence, is we could set up a little chat server, but we are running out of time. So half of your work for today is to connect to a TCP server that we're setting up. It'll be actually running on a Raspberry Pi, and it'll be running on our network, and you're going to write a little TCP client to connect to it and interact with it. Now, the interesting thing, because we haven't talked at all about HTTP yet, which is where we usually use, yes? A Raspberry Pi is a microcomputer. They like to say about the size of a credit card, but it's more like the size of your entire wallet. And if you're interested, they're hanging on the back of any of these TVs. They're roughly about that size, probably 4 inches by 3 inches. And they have a CPU and a GPU, and they're essentially just tiny computers. And they're great for setting up little networks, for running little applications, Internet of Things, stuff like that. There's one hanging behind this, yeah. And there's one probably hanging on that TV as well. And so what you're going to do is you're going to write a little client, a TCP client, to connect to that. And it's a snake game. So you're going to write a little client that you'll be able to use WASD to move like a snake cursor around the screen. And you'll all be able to connect to that server, and then you'll see all of your snakes driving around that screen. Okay? So one of the interesting things about TCP, if we jump back to here, is all it does is establish how your data is going to be transported over a network. That's all TCP does, which enables other people to write libraries and standards on top of that. Because all this is doing is saying, I'm going to bring in a header, I'm going to establish a connection using the three-way handshake. If missing packets don't get there, I'll resend them. Packets are guaranteed to arrive in order. There's nothing about this that says, you know, anything beyond that. So we can write our own layers on top of this using TCP. So when you connect later today, to the Snake server, you're actually going to be running your own protocol that we have created to run on top of TCP. And you're going to send strings over the wire that are going to be interpreted from the server, and they will act on that as, so you send W over, and it interprets that and moves your snake up a pixel. Okay? So you can actually write your own standards, but luckily for us, much smarter people have already written their own standards. And one of those standards that utilizes TCP is what's known as HTTP. Again, you can probably guess what the P stands for. This is very common. Does anyone know what the H, T, and the T stand for? That's correct. Hypertext Transfer Protocol. Hypertext is how the internet works. Anchor tags, if you're familiar, if you've done any HTML, anchor tags have hrefs. That's a hypertext reference. The way that the internet actually works is a whole bunch of links that go to different pages in an interconnected network. Those are hyperlinks. So HTTP is the Hypertext Transfer Protocol. And it works on top of TCP. So it lives in these layers here. It actually lives in the application layer. This is where HTTP, HTTPS, SSH, SMTP, if you're familiar with like the simple mail transfer protocol, this is where all of these protocols live. And again, what's the goal of these protocols? Is to turn whatever information you want to send into ones and zeros. That's the entire goal. But if you use HTTP, to send your communication, that will look different than HTTPS. Those will be different ones and zeros. HTTPS, they'd be encrypted. If you use SMTP, the Simple Mail Transfer Protocol, those will be different ones and zeros. If you use FTP, the File Transfer Protocol, again, different ones and zeros. The whole purpose of these 3 layers is to create ones and zeros to send over the network. Okay? So we know that HTTP lives in the application layer, and we know that it uses TCP under the hood. Okay? So what do we know about TCP? We know that it requires that handshake, right? So any protocol that's written above that is going to utilize the same system. So HTTP uses a request and response system. Okay? Nothing is unbidden. No, you don't ever start your computer up and Google goes, hey, here's some search results. That's not how the internet works. That's not how HTTP works. Okay? HTTP works in a request and response. You make a request of another machine for some data, and that machine sends back a response. Okay? And these requests are what is known as stateless. There is no memory, I'll make this a little bigger, no memory of previous communication. So when I go to google.com and I put in a search, and it sends me back those search results, and then I send another search, it doesn't go, oh, hey, I remember you from before. It says, I have no idea who you are. You asked me for some information, and I'm going to send it back. Does that mesh with your idea of how the internet works? But does it actually? What happens when you visit Google Drive? Do you have to log in again? What happens when you visit Facebook? Do you have to, if it's stateless, and it has no HTTP, I'm definitively telling you, is stateless. It has no memory of prior communication. But if you go to facebook.com and you've already logged in yesterday, you don't have to log in again, right? So how does that work? It doesn't actually remember you. You have to send along additional information that says, hey, remember me from yesterday, I was here. Yes? It does. It can use cookies, it can use tokens, it can use session storage in your browser. The purpose is that when you send along a request, sometimes more information is sent along as well. And we'll actually you'll build them out over the course of working your way through Compass. Not necessarily this week, but we will touch on cookies and sessions and things like that, and how to make a server remember who you are. But the key is, the server does not have any memory whatsoever of who you are or your previous communication. You literally have to send over, when you connect to Facebook, you send over your credentials again. You send over and say, hey, I'm already logged in. And then it goes, oh, you're logged in. OK, I can show you your homepage. But it is completely stateless. HTTP, totally stateless. So we communicate over TCP using what are called routes. And routes are made up of 2 things. They are made up of a method, some people call it the verb, and a path. Okay, so path, you're probably more familiar with. Path would be, that's a path. In other words, on this host, show me slash whatever, my page. Okay? You go to cutekittens.org/12, and that'll show you the 12th cute kitten on cutekittens.org. Okay? So this is the path that we're talking about. But there's another portion that it's made up of, the method. And we are given various different methods that we're allowed to have. We have GET. So whenever you make a request in your browser to google.com, let's say, every request, man, that's gigantic. Every request is a GET request. Every single time that you type something in here, you're saying, I want to get the data that you're serving back. And so the Google server gets this GET request to google.com, and it responds with, here's your HTML and your CSS and your JavaScript to load the search page in your browser window. And then when you make another, you want to look for TCP jokes, again, you're making another GET request to the server, and the server is responding. So this is why we call it a GET request, because you want to get something back. Okay? We also have POST, which you've probably heard of. GET and POST are the predominant methods on the internet. POST is how you send information. If you have like a login form or something like that, you want to send over the username and the password to the server to see if you can actually log in, if your credentials are correct. You would make a POST request in that case. You want to send data over, okay? We also have some other ones. We have put, patch, and delete. There are a couple other ones. These two are the primary ones. Put and patch have to deal with updating information. Do you want to put information into the database? Do you want to create some new information? Do you want to patch some information that's already there, as in update it in place? Like, oh, I changed my home address with my credit card. You would send a patch request to update your address in their system. And you can probably guess what delete does, what a delete request does. But in HTTP, and HTML, we predominantly have GET and POST, okay? The vast, vast, vast majority of the requests that you're going to make will be either GET requests to get information or POST requests to send information. Does that make sense? Okay. What else do we have? Yes. Okay, so our requests are made up of a header and a body. So the header will contain, remember when I said that all the underlying, when they break it up into packet segments and packets, they include an origin and a destination? Well, HTTP says that the header contains an origin and a destination. That's how the protocols below know how to route your data, and how Google knows how to send the data back to you when you make a request. So it has a header. Let's break this out on 2 lines. It has a header, which contains an origin, a destination. It might contain things like content type. Like when you make a request and you get back HTML, it'll say this is text/HTML. In other words, how should I decode it on my side? If you've heard of JSON, JavaScript Object Notation, that's another content type. XML is another content type. CSV, anything. You can send any kind of data back and forth on the internet, but it all comes over as text, as ones and zeros, and you need to say, this is what it is. So that will live in the header. You'll say, I want to make a request, and I want you to send it back in the following format. Okay? This is where your cookies would also be sent. They'll be sent along in the header. This is where extra parameters. So if you see up here, I don't know if I can actually make this bigger. Okay, if you're familiar with query parameters, get off of there. I don't want the tooltip. Okay, so we see we have, hopefully you can actually see that. There we go. Google.com/search, and then we have a question mark, right? And then we have source equals HP, EI equals something, something, blah, blah, blah. Let's see if I can move along. Hey, there we go. Q. That looks fancy. Q equals TCP plus joke. Well, that's the query that I typed into Google, right? These are what are called query parameters. They show up in the URL. These will also be sent along with in the header of your request. That's how Google knows to respond with TCP jokes. If I zoom back out for a second so we don't jump all around, and I get rid of everything else. I know I said we weren't going to talk about hacking, but okay, this is what's known as URL hacking. So I could use the interface how it's supposed to be used, or I can use it how I want to use it. Okay, so I don't want to see a TCP joke. I want to see a UDP joke. I didn't use their form. I passed that along, oops, as a query string parameter. Does that make sense? Okay. So all of this stuff is in this header. Okay. Then we also have a body. And usually not used in GET, but this will be where your post information lives. Okay? So if you send along a new user gets registered, this will be their username, their name, their email address, everything else that you collected with that form will get sent along inside of the body of the request. So if you hear, oh, that's in the request body, this is what they're talking about. Each request has a header and a body. Okay? So that's half of it. That's how we make requests for resources. Then we get responses from the server. And the responses also have a header. And this will have things like origin and destination, right? If anything gets lost. Content type, content length. So in other words, how much content am I sending to you? Things like that. We have all of these inside of the response header. And we have a response body. And guess what's in the response body? That's going to be your content. So if you make a request to a website to give you back HTML, CSS, and JavaScript, then that's what's coming back over in the body of the request to your browser. What else do we need to cover? Status codes. Ah, yes, of course. So responses have status codes. So things happen so often on the internet that they standardized a way of reporting when something happens. Does anybody know any famous status codes, HTTP status codes? Sorry, 404? 200. Okay, what does 200 mean? 200 literally means okay. Everything went great. I understood your request. It was valid. You're allowed to see that information. Here's the information as it comes back. Okay. What's another one that we'll see? 302. Oh, 404. There we go. Resource not found, right? You make a request to a website and there is no web page there. Well, then that server is not going to say 200 okay. Here's my best shot. It's going to say 404. I don't know what you're talking about. Here's another one that you'll probably see a lot. Yes, everybody's favorite, 500. That means something has gone wrong with the server. And these actually fall into categories. So we call these like 2XX. So we're saying that's like a 2 and whatever happens afterwards, we don't really care about because 200 series means everything's fine. There's a bunch of different 200 series codes, but they all mean everything's fine. 400 series codes mean there's some kind of problem with your request. Either you asked for an endpoint that doesn't exist, or you might see this one a lot. If you're trying to visit protected endpoints and you don't have the proper credentials, you'll get a 401 back. You're not authorized to see that. But again, that falls into the 4XX series. And the 5XX series are big time errors. That means the server's down, something terrible has happened. Okay? If you see that. And of course, my favorite place to get this is HTTP cats, where you can visually see all of these response codes. So we have 200 OK here. Apparently that's a cat saying OK. 202, your request was accepted. Let's see, what are some other famous ones that you'll see? 301, resources moved. If you migrate servers or something like that, you can actually tell your server to say, anybody makes a request for this page, tell their browser it actually lives over there now. And so you'll get back a 301 from the server. That's been moved. Okay. Let's see what they've got for 403, forbidden. I'm not sure why that equals forbidden, but there you go. 401, not authorized. No cats allowed, apparently. 404, not found. So if you ever get a job interview question about HTTP, just respond with a cat meme. Okay. This is one of my favorites. This is actually a valid HTTP code. It's code 418, I am a teapot. Well, you can set up your servers to send any kind of response code that you want. So you could, in theory, respond with 418, I am a teapot. We also, now that it's legal, 420 is also a valid HTTP response. Enhance your comm. Unprocessable entities, let's scroll down to the 500 series. You see how these are all kind of like together? Like all the 400 series say there's something wrong with your request. That resource isn't found, you're not authorized to see it, you haven't sent along a length. 500 series, things have gone wrong. Internal server errors, bad gateways, services are unavailable, insufficient storage. All of these mean something. And when you get these responses back from a server, you will actually write code to listen for these errors and handle them in certain ways. And the way that you do that is every single response that comes over HTTP has a status code. Every single one. If you don't explicitly say it on your server, it will be implicitly done by the server because HTTP, that protocol says, every response has a status code, okay? Response headers and response body. Okay, looks like we covered everything that we need to do for HTTP. We did a tiny little demo. We covered HTTP fundamentals. Do we have enough time? It is 12:01. We could create a little HTTP client, or I could try and convince you that this is how the internet works. And I think the easiest way will be to open our dev tools and look at our micro font. Okay, so we're in the dev tools. And we're going to go into, if we wanted to see what kind of communication is happening over the network, we go to the network tab. Dun, dun, dun. Okay, so this is our network tab. This shows us every resource that happens, every request and response that happens when we visit a web page. So let's refresh this. And we'll see, OK, check this out. Our request came back with way more information than what we asked for. And the reason why is because the HTML that came back contained inside of it a whole bunch of little requests. If you have an image element with a source attribute inside of it, that source is actually making a GET request to that source. So you see the little board over there, it says image source equals and then funny picture, or funny image or something like that. That would actually make a GET request for that resource. Okay? And that's what's happening here. So every single one of these images, if I click on this, we'll see that this is a thumbnail image. Is there actually an image tag? Oh, it looks like they're using a library. But if we could actually see the image tag, they would be loaded from there. So let's jump back to something that we actually recognize as JavaScript. Let's look at some JavaScript. And we can actually take a look at the headers. OK, so we made a request. So that request has headers. This was made by a Chrome extension. The request method was get. The status code was 200 OK, right? There's some kind of refer policy that goes along. And then we have some response headers. Access control origin, allow origin. This will be for cores when you get to deal with that, but you don't need to worry about that right now. But you see that the request has its own headers. The response has headers. Oh, here's our request headers down here. You see user agent. This is pretty funny. So hopefully that's big enough in the back. So every single request on the internet comes along with a user agent, which says, what agent am I using? And originally you would say, I'm using Chrome, right? From within Chrome, you've got a user agent, and the user agent is Chrome. What started happening is that server developers started writing specific things to happen for specific browsers. So if you said, I'm using Firefox, it would give you a different experience than if you were using Chrome or Internet Explorer or Safari, right? So what developers started doing, browser developers, found a way around that. And they said, you know what? I'm Mozilla 5.0 on a Mac. But I'm also Apple WebKit. I'm also Chrome. Oh, and I'm also Safari. So this is just a little aside, but your user agents, every browser says, I'm every browser. Give me the best possible user experience. So it was originally for you to be able to say which browser you were connecting from, but it's now just become a dump. You'll see this in every single browser. They just list every browser manufacturer. They say, I'm all of them. Give me the best possible experience. OK, so clicking on preview gives us a preview of the response, and this will make a lot more sense with an image. So let's look at this. We made a GET request, request URL. Remember when I said that every HTTP request has a path or a URL and a method. So we made a GET request to this URL. And if we cut this out, we can actually go into here and paste that in, and we'll see that image right in our browser. So again, we made another GET request. Status was 200. Here's the remote address over 443. So it was made an HTTPS request, OK, over port 443. The response header came back with a bytes, a maximum age, what type it was. The content type is image/JPEG, the date, when this expires. In other words, if you make another request to the same URL, use the one that you've cached. You don't have to load that image again. So if I make this request again, we'll actually just load the one from the cache. And it'll actually come back much faster. Because your browser caches web pages to help make your browsing experience faster. Okay? So instead of making the request to the server every single time, we're just going to say, no, use the one from the cache. Okay. Last modified. This is how it knows whether or not the page needs to be refreshed. It checks this last modified. And if the last modified changed, then it knows it needs to request a new. So we see our request headers. And then here's the preview of the response. We can see that right in here. And any cookies that were sent along. Also, any timing. So everything that we do inside of the browser is an HTTP request. It's either going to be a GET or a POST or a put, patch, or delete, but the majority of them use GET and POST. Every request has a header and a body. Even GET requests have bodies, but they're never used, and that's by convention. You could put something in the GET body, but most of the time the server won't be listening for any kind of body. And responses have a header and a body, as we already saw, and every response comes with a status code. OK? So we can see how HTTP utilizes TCP. Hopefully that's clear. Under the hood, it's a lower level protocol, but it's utilizing the strength of TCP and the reliability of a secure connection that we know the connection has been established using that three-way handshake. And we know that anything that gets lost along the way will be resent because the client will say, hey, I didn't get that, send it again. Okay? And this is how modern information travels over the internet. Okay? So yeah, this is definitely the most conceptual lecture, I think, that I've ever given. Hopefully that wasn't too boring. And I hope you enjoy your TCP snake this afternoon. Does anybody have any questions before I let you go? Yes? It's inside the browser. Your browser is actually caching that information. And you can actually request that the browser, you know when you go in and you say, delete all my cookies or delete all my history, you can ask it to clear your cache as well. Sorry? Yeah. Yeah. It depends on what it is. More than likely, you'd then get some kind of network connection error. But you could, in theory, be able to load parts of that information. One thing that I always think is kind of humorous is when someone disables right-click on an image. And they say, no, that image is copyright or whatever. You can't download that image. Well, if the image is in my browser, it lives on my computer. And we can see it right here. So anything that gets sent over the internet, if you can see it on a page, it lives in your machine. Okay? Hopefully that answered that question. Anything else? Are we good? Okay. Enjoy Snake. And if you think of anything, I'm available on Slack. I'll also be mentoring this afternoon. Thank you.